file, we want to get the magnetic field due to a loop of current along the axis of the loop. So it's also kind of an easy problem to do. There's going to be some simplification that will make it easier to do than a general problem. So let's review first the Biot-Savart law. If you have a wire and it has the current in it, if you want to get the magnetic field at a point, you get the magnetic field due to each element of current given by this formula, and then you integrate to get the whole magnetic field, the total magnetic field at point P due to the whole wire. So what we did before, we had a loop of current and we got the magnetic field only at one point in this problem, at the center. What we're trying to find now is the magnetic field everywhere along the central axis. So you can see that the simple thing that happens is that the magnetic field is pointing along the axis. So it's easy to get. It doesn't have a component off the axis. So that's going to make it easy to relatively to get. And we're going to focus now on getting that magnetic field. So this is a drawing of the problem in 3 dimensions. The ring of current is put in the YZ plane, and the perpendicular axis, which is the x-axis, is perpendicular to the ring, and this is the origin. The center of the ring is at the origin. And the point P where we want to find the magnetic field is along the x-axis at a distance x from the origin. The current is going in this direction, as shown by the arrow, and the question is asking what's the magnetic field value at this point, at an arbitrary point along the x-axis. If we start thinking about the problem by looking at what the magnetic field direction would be due to an element of current at the top of the ring. So take ds then to be along this direction, which is in the z direction in this case for the top element. The r hat unit vector, remember, it points from the element to the point where you want to find the magnetic field. So the r hat vector points this way. The angle between them is 90 degrees. If you can't imagine that, try to imagine it a bit more. We're going to look at the problem now from a different vantage point. What if you stand here and you look in this direction, in the minus z direction? What would you see? You'd just see a line here because you won't be able to see the shape of the loop, but you'll just see a line, and the ds unit vector, the ds element of current will be coming out of towards you. It will be coming towards you, and the r hat vector will be going a bit down to the right. So let's do that. Let's look and see what happens if you look at the problem from this vantage point, looking in the minus z direction. This is what you would get. So remember, the loop is now in a plane perpendicular to the screen, so you can't see the loop. Here the current is coming out of the page. That's the element of length that we were talking about at the top of the loop. And the r hat unit vector points from the element of current to the point where you want to find the magnetic field. This is the point P on the x-axis. So the angle between them is 90 degrees very clearly because ds points out of the page and r hat is in the plane of the page. So the angle is 90 degrees. So what's the direction of the magnetic field due to this element of current at the top of the ring only? If you take ds out of the page and take ds cross r hat, you can show that the direction of the magnetic field should be perpendicular to the r hat unit vector and perpendicular to the ds vector, and it will point in this direction. So it's not perfectly along the y-axis, it's at some angle, but it has a 90 degrees with respect to this line over here. Okay, why is that important? Because if we take an element of length exactly opposite the original one, this one, now the ds is going opposite direction than the other one, and the r hat unit vector points from the element of current to the point P. If we look from the same vantage point that we did before, standing here and looking in the minus z direction, this is what we will see for that element of current at the bottom. The element of current now here points into the page. And the r hat unit vector points from the element to the point where you want to find the magnetic field. So what's the direction of the magnetic field due to this element of current? If you get ds cross r hat, you can show that it points in this direction. It's at 90 degrees with respect to this line. Now, if you put both magnetic field vectors due to the top element of current and the bottom element of current, you can see here why we're trying to do this exercise, because the components in the y direction in this case will cancel out. Basically, the components parallel to the loop will cancel out. The component perpendicular to the loop will add. So why is this important? It's important because then before you solve the problem, you know that you only need to calculate the component of the magnetic field along the x-axis. You don't need to calculate the one that's perpendicular to the x-axis, because you know that it's going to always cancel out every two elements of current. The magnetic field due to them in the direction parallel to the loop will cancel out. So the only magnetic field that will exist is one along the x-axis. So that exercise then makes the problem easier for us to tackle. So let's first look, what is the magnitude of this magnetic field due to this element of current right here? Well, we know that the magnitude is the magnitude of ds, the magnitude of r hat, which is 1, times sine of the angle between ds and r hat. The angle between ds and r hat is 90 degrees, so we get sine 90 is 1, so this is all what we get. This is the magnitude of the magnetic field, which is the magnitude of this vector, which is the magnetic field at this point due to this element of current. Now, we just showed previously from the symmetry argument that we only need the x component. So how can we proceed to get the x component of this? Clearly, if you have any vector and you want to get its x component, dbx, you take db and you multiply by cosine theta, where theta is this angle. So dbx, which is what we want, is db times cosine theta. db is this, and there's the cosine theta. So this is now the component of the magnetic field in the x direction. It's still due to only this element of current. It's not the total magnetic field. All this is just the magnetic field in the x direction due to this particular element of current. Now, when we come to rewrite things, we can see that cosine theta, if this angle is theta, and this angle is 90 degrees, as we know, and we call this angle alpha, then alpha plus theta should be 90 degrees. But if you look at this triangle, this also is 90 degrees. So alpha plus this angle is also 90 degrees. That means this is also theta. So this angle is exactly the same as this one. So if you want to replace cosine theta and write it in a different way, we can do that by writing cosine theta as the adjacent, which is r, the radius of the ring, over the hypotenuse, which is small r, which is the distance between the element of current and point P. So cosine theta is r over r. So we can do that substitution, and then you notice here that you have an r and an r squared, you get r cubed. And so you get this for the magnitude of the magnetic field, the x component of the magnitude of the magnetic field due to this element of current. Now, we got dbx. So what do we want to do? We want to get the total magnetic field in the x direction due to all the elements of current. So we want to now integrate over the whole loop. So we put the integration, and now think, what are the variables and what are the constants? If you go from different element to element on the loop, is big R different? No, big R is just the radius of the loop. It's a constant. I is a constant. Mu naught is a constant. 4 pi is a constant. Is R a constant or a variable? R is the distance between the element and the point P. If you go to any other element on the loop, the distance is exactly the same from any element to point P. So R is a constant. So you can take everything outside of the integration and you get integration of ds. What's integration of ds? You're integrating all the elements of length along the loop, which will give you the circumference of the loop, which is 2 pi r. So if we simplify we get this result for the x component of the magnetic field. Now this is the total magnetic field in the x direction. But remember, we want our result in terms of x, not in terms of r. So can we replace r by x? Is there a relationship between r, x? Yes. So look at this triangle and we can see that r is the square root of x squared plus r squared. But we don't want r, we want r cubed. So we get r cubed is x squared plus r squared to the power 3 over 2. So now we can substitute r cubed here and we can find the result that we want, which is the magnetic field as a function of x. So this is bx as a function of x. So as you see, if you go to farther and farther points along the x-axis, x becomes larger, the magnetic field gets weaker. So So this is the summary. This is the magnetic field at point P, which is located at some distance x from the center of the loop. And this is the x component of the magnetic field, and there is no other component of magnetic field. As long as you're on the x-axis, the magnetic field is always in the x direction. We can make some simplification, some special conditions. What if you want to get the magnetic field at the center of the loop? And we did this before, so we can compare now the result we get from the new formula with the one we got before. To get the magnetic field at the center of the loop, we simply put x equal to 0. When you put x equal to 0, you get r squared to the power 3 over 2. R squared to the power 3 over 2 is r cubed. R cubed, and you have an r squared, you get an r. So this is exactly the result we got before, mu naught I over 2r. So this confirms that we've been doing the right thing in the previous derivation. And also we can get another limit, special case, if the radius of the ring is much smaller than x. For instance, let's say the radius of the ring is 1 millimeter and x is 1 kilometer. Then in that case, you can completely neglect this r in the denominator, and you have then x squared to the power 3 over 2, which is x cubed. So this is an approximate formula for the magnetic field at any point x, where x is much bigger than the radius. You can watch this video to see how the magnetic field looks like due to various coils.